So if you want to fold a strip of paper in half, what do? You match the ends up and you fold it, right? And then if you want to do quarters, well, okay, you've got a half point now, so you can just, fold into the middle, fold to the half. You've got quarters, okay? And now you've got quarters, so now you can do eighths, right? I tell you any power of 2, you can fold it like that, right? 2, 4, 8, 16, whatever. Okay? 32, 64, 8,192. How many of you played 2048 on your phone? How far have you gotten?
Not far. I think one time I got 2048. That was like 3 years ago.
So I managed to get to 8192 one time. You can, in fact, keep going. Okay, so now, fine. Powers of 2. We all agree we can fold a piece of paper into powers of 2. What about fifths?
Probably. I searched this up.
That's hard. That's hard. You have to get out a ruler and stuff.
You have to get out a ruler and stuff. Okay, well, one thing I like to do in my spare time is to fold origami. And there are exact methods to fold a paper into fifths. But I want to tell you something today. It's an approximation method. It's called Fujimoto Approximation. Fujimoto is a Japanese, well, you'll see. So we're going to fold this into approximate fifths, okay? But approximate, exact, even if I told you how to fold it into exact fifths, how would you know?
Huh?
How good is your ruler? Yeah, that's just it. You don't know. Exactly. That's the point. Okay, so here's the algorithm. You guys know about algorithms a little bit. What you're going to do is you're going to make a guess. That's why it's called approximation. You're going to make a guess. So just look at this strip of paper, and wherever you think a fifth is, roughly, make a little fold. But don't fold all the way across. Just make a little pinch like that. Don't fold it all the way across the paper. Just make a little pinch on the top. Okay? So this is what I think a fifth of this is, roughly. I don't know. There's no right answer here. Okay? Just make a guess. Okay? Now, here's the algorithm. I think I made a guess that this is 1/5. Okay? So I'm guessing that the rest is how much? Okay, is 4 odd or even? It's even. So I have 4/5, I think, over here. I can fold that in half, right?
Whoa!
Okay, now don't fold all the way across. Just make a pinch. Okay? Now I've done nothing amazing yet. But now, okay, now I've got a little more stuff going on here. How much is over here on this side now? 2/5. Is 2 odd or even?
Even.
See, now if I start with an odd number of things, at any given time, I have even on one side, odd on another, right? So I think I have 2 over here. Okay, great. Make another little pinch. Okay, so now I think this is 1/5. How much is over here? What do I do?
Fold it in half.
Fold it in half.
It is like a little sandwich.
Okay,
Nom nom nom.
fine. Now I think this how much is 2/5, right? Fold that in half. Now if you guessed, so yeah, now if you guessed well to begin with, you're back where you started, except I'm not, okay? So you probably can't see, but my original fold, my original guess is right there. Now I'm back to this being what I think is 1/5. Okay? So let's think about this for a second, okay? If I had guessed correctly to begin with, I'd be exactly back, okay? But I wasn't. I was off a little bit. So now what can I do? Well, now I've got an updated idea of what I think 1/5 is. So I run the algorithm again. I now think that this new mark, I'll treat that as a guess, and I start again. I've got 4/5 on this side, so I fold, make a little pinch. Okay. Now I think I've got 2/5 over here. Make a little pinch. I've forgotten which one it is. Wait a minute. So let's see, this guy. Hold it to this guy. Okay, good. And now to this guy. Okay. And now I think I have 4/5 on the right again. So I fold to that. And then I think I have 2/5 again. So I fold it again. And okay, now we're done.
I'm getting the same thing.
You're getting the same thing, or really close. When you did it again, you got back to where you almost were the first time, right? That's 1/5. Make all your folds sharp. You're done. Use that, so fold all the way across.
Wait, I'm gonna do it again.
That's
Is that
cool.
what the other paper's for?
No, but you can do it again. I got plenty of paper. Do it all you want. I brought plenty of paper. We're going to do other numbers too. We're not just going to do 5. 5's boring. Yeah.
What if the number minus 1 isn't a power 2?
We'll see. You're right. I mean, that's a good question. These are all good questions. So once you make all your folds sharp, now you've folded this thing into fifths. Any idea why this works?
It's made by an Asian guy.
Why do you think this works?
I don't.
Science.
Science? Yeah? What do you think?
Because the algorithm just goes again and again. You just keep putting closer and closer and closer.
Yeah?
It looks exact.
Yeah? Why do you keep getting closer, do you think? Yeah.
So if you're off by a number n,
Mm-hmm.
you make the 4 more sections, so you divide that number n by 4.
Mm-hmm.
And then now you are only off by n over 4. And then you repeat the process so you can get infinitely close to 1/5.
That's actually very close to being the right answer. That's you're absolutely on the right track. I mean, that's sort of the whole idea, right? I made a guess. And this guess, I think, is 1/5, but maybe it's off by a number, and I'll call that number E, right? Maybe I'm a little big, maybe I'm a little small, I don't know. Okay? What happens when now my next step is I make this fold, and I'm going to make a fold right here. And that's what I think is 3/5. But now how far off am I? Half of E. Right? I've cut my error down in half already with one fold. And then I do this bit. My handwriting's terrible, sorry. And then I do this fold. And then when I do this fold again, I'm back to what I think is 1/5, but now I'm off by at most E over 16. Right? So every time I make a fold, I'm cutting my error in half. And what do we know about cutting things in half?
He makes it small.
It makes it small. Eventually, right?
Yeah,
It'll be so small that you can't see it. And by the way, if I kept doing this again, that's why when we did it twice, when we run through this one more time, we come back to E over 32, right? And E over 16, no, sorry. Thank you, not 32. This would be 32, sorry, it'd be 32 here, 64, 128, 256, right? So, okay, already E over 256 is what, effectively?
Really small.
It's 0, right?
Tiny.
I mean, E isn't very big to begin with. You divide it by 256, it may as well not be there. You can't see that with the naked eye, okay? But the thing is, if E was small to begin with, E over 16 and E over 256, whatever, they're both very small, okay? So that's why this method works. Cool. Isn't this cool? Now, this is why you don't want to bother with exact algorithms for folding pieces of paper, because there's error no matter what you do. And if you ever start folding origami, which I really recommend because there's a lot of cool math in origami. It is fun.
And it makes you happy.
And it does. And when you fold, often what happens is your error compounds. It adds up. Whereas with this, it cuts down every time. And that's why it works. Okay? Now, I didn't want to just show you this cool thing for folding paper. Right? There must be some math behind this other than you're just cutting the error in half every time. All right? So let's try, let's remind ourselves, what was the sequence of folds that I made? Okay? So I started with 1/5. And my first fold, I'm going to say I folded the right side to this. Okay? And then what did I do? So I folded to here, and I thought I had 3/5 here, so I had 2/5 here, so I made another right fold. Okay? And then I had this line, and then I thought, oh, I've got 4/5 over here, so I made a left fold. And then I had 2/5, I made another left fold. Okay? That was the sequence of folds we made. Right, right, left, left, and then we repeated. Okay? All right, let's do it again, but not with 5. So this was n equals 5. This method works for any odd number.
What about oh wait.
Evens, okay, all right. So let's think for a second, okay? If you hand me any even integer, and I want to fold it into even pieces, what would I do?
What if the integers fold the paper into -2 pieces?
That's true. Positive integers. Thank you. So if I wanted to fold something into 14ths, what would I do? I'd fold it in half first, and then fold each side into 7ths. Okay. And now, what about
Wait a
say?
second. If you had to fold it into 7ths, you'd
Yep.
also have to use that, wouldn't you?
Yeah, you would, but each side, right? So treat it like it's just like 2 pieces of paper now. Okay. You could do it that way. What if you wanted to fold it into like 15ths? So that's 3 and 5, right? So you could fold it into thirds, and then fold each of those thirds into fifths. So I'm really going to worry about prime numbers, okay? You can do this for any odd number, but let's just think about prime numbers. So
Prime numbers are scary.
so my next favorite prime number after 5, of course, is 7. All right, so let's fold it into 7ths. Let's do the same thing, okay? So you're going to make a guess of where you think a 7th is and make a little pinch. So I'm just going to do this, okay? So now I have 1/7. So that means I have 6/7 on this side, right? That's the even side, so I'm going to fold this, make my little pinch. Bless you. Okay, so now I've got this pinch here. How many are on this side? 3, so I have 4 over here and 4 on the left. So now I'm going to fold the 4 into half. Okay? And now I think I have 2/7 over here on the left, so I fold this again to get it. And now I've updated what I think 1/7 is, and I actually made a pretty good guess. I'm pretty close as it stands. I'm not very far off. Okay? And then you just do it again. Doing it again will finish it off. If your first guess was good, then you're good. Here we hit every line. We didn't hit every line here. We'll talk about that later. Okay? But fine, but I've got a 7th now. Okay? So that's 1/7, and then I can get, then I can get the rest. When you only end up making 3 creases here, and what's interesting about that is then how do you get the rest? How do you get the rest of the 7ths? Well, you can make it happen.
2, 3, 4, 5, 6, 7.
This area here represents 2/7, so you can just get those creases on top of each other and fold that in half. Or you can start to compound things. It's you can use the other folds to help guide your folds, and you can get 7ths. Okay. Yep. You achieved 7ness. Okay. Now this was different, right? This was fundamentally different than the fifths. So let's run through it on the board. Let's see what happened. So I made a guess of what I thought 1/7 was. So that meant I had 6 over here. I folded that in half. Okay, so this line would be 4/7. Now I have 4 on this side, so I would fold over here, and then I get 2. Oh, and then I would fold again, and I'd get to 1, and I'd stop. Right? So you make your guess. That means you have 6 pieces over here. You fold that in half. The middle of that is 4. Then you would fold this side in half. The middle of that is 2. And then you would fold that in half, and that's 1. And you just keep repeating that. Okay? So I didn't hit every crease. That's one interesting thing to note. What was my sequence of folds?
You started from 1/7.
So I made a right fold. Yep. And then what did I do?
You then folded
A left, and then another left. Okay? And then I repeat. So here I went right, right, left, left. Here I went right, left, left, right, left, left, right, left, left. Okay. Okay. So let me try to throw a little more math at this. And I'm going to talk about binary. Well, I'm going to call them decimals, although decimal implies 10, right?
Yeah.
Oh, that's a decimal.
Okay.
They like sound like
So in base 10, what's the decimal of 1/8? Yeah.
0.8.
0.125, right? So that's 1/10 plus 2 over 10 squared plus 5 over 10 cubed, right?
What?
Yep. Okay. That's what decimals mean, right? Each place is 1 over 10 to that power. Okay, so this is 1/10 plus 2 over 10 squared plus 5 over 10 cubed. Okay, fine. What's special about 10?
It's made of 10 numbers.
Why is it easy to work with?
It's the base of our number system.
Why is it the base of our number system?
Because of
Because we have
capitalism.
Because we have 10 fingers. It's that simple. Okay?
Oh, toes.
Well, so we could do base 20 if we want, but toes are inside your shoes and your fingers are always out. So you got 10 fingers, we use base 10. There's nothing special with that. What if we had 2 fingers? Okay?
Base 2.
We would do binary. The thing is, you might not be used to this, but you can talk about fractions in binary all you want to. Okay? And it works the same way. So how many halves are there in an eighth? There aren't any.
3.
No, there aren't any, right?
Oh, wait.
Just like 1/8 is bigger than a tenth, right? So there's a tenth in there, and so on. How many fourths are in there? None. No, we don't want negatives.
Wait, no.
And then there's 1/8 in there, right? So it's 1 over 2 cubed. So here in base 10, we would write 0.125. So I might write parentheses and a 10 to tell you that I'm in base 10. In binary, that's what it looks like. In binary, you can only have zeros and ones. Okay?
Equal.
Right? Zeros and ones, that's it. Okay.
Oh, that's why they call it the binary code.
So, what's 1/5?
2.
0.2.
In decimal, in base 10, it's 0.2. What is it in binary? Okay,
Wait a second.
so let's think about this.
0 over 4 plus.
How many halves are there?
None.
None. How many quarters? None, because 1/5 is less than a quarter. Okay. There is an eighth, though. 1/5 is bigger than an eighth.
Some.
How many sixteenths? I don't know. Let's see. Let me go back to base 10. Let me subtract. 1/5 minus 1/8 is 3 over 40, right?
Probably.
That was fast. Yeah. Stop.
Is that bigger than 1/16 or less than 1/16?
Well, what is math?
How are we supposed to know? We're like 10.
1/16, yeah? It's bigger, isn't it? Yeah. This is bigger than 1/16. Why is this bigger than 1/16? If you put a 3 in that numerator, it'd be 3 over 48. Right? So 1/16 is 3 over 48. This is 3 over 40. That's bigger. Okay? So there is a 16th in here. Okay? Okay. So now, 1/5 minus 1/8 is 3/40. What's 3/40 minus 1/16? A common denominator here is 80, right? So this is 6 over 80 minus 5 over 80, which is 1 over 80. 1 over 80 is 1 over 5 times 1 over 16. So this repeats. It is a repeating decimal, or in binary.
It is.
1/5 in binary is 0.0011, 0011, 0011 forever. Repeating, yeah.
Like
You can expand in any power, any base that you like. Yeah. Any integer that you want. Yeah, actually.
Why binary is evil.
Oh,
No binary.
So 1/5
It goes on forever.
Now,
You're
in-
just
in-
scared of the unknown.
in base
It's like a
10,
woolly pair, it's like a
right?
dog.
In base 10, 1/5 is 0.2. It stops. Okay? But in binary, 1/5 is a repeating decimal.
5-nary.
It'd be 0.1. That's it.
Cool.
Yep.
It'd be
Okay.
cool now.
Now, let's see. What was my fold sequence for 1/5? Right, right, left, left.
Yeah.
Evil.
Oh, the right is 0.
So you think right is 0 and left is 1. Okay, well, let's do 1/7. So this is our working conjecture. Let's say this is our conjecture. I don't know if we're going to prove this or not, but let's see. All right, what's 1/7 in binary? So there aren't any halves. There aren't any quarters. What is, it's an eighth, right? And then let's see, 1/7 minus 1/8 is
Something.
1/56, which is 1/7 times 1/8, so it repeats. So this is 0.001
No.
repeating, base 2.
Then it's wrong. When we wrong.
wait. What if you have to take it backwards and L equals 0 and R equals 1?
What if you take it backwards and L is 0 and R equals 1?
Then it's like that for a certain number. What's the difference between 5 and 7? What's the difference between 5 and 7?
So our fold sequence for 1/7 was right, left, left. Our fold sequence for 1/5 was right, right, left, left. That's the new. So this conjecture doesn't work because 1/7 didn't work. We have two pieces of evidence for this conjecture.
We do?
Yeah, it works for both of them, for 1/7 and 1/5. That's not a proof. Okay. However, I will tell you that is correct. Okay. I'm not going to get. I don't. We're not going to prove this, but it can be proved. It's actually not too terrible to prove, but let's not right now. Okay. So this is how it works. You think of R as being 1, left folds being 0, and you go backwards in the repeating expansion. Okay? Now, what I think is kind of fun about this is that you can now figure out the binary expansion of any odd fraction folding a piece of paper. Like, I figured this out using awful fraction arithmetic. Who wants to do that?
Maybe somebody who was bored.
Well, yeah, I saw some hands in the back. Okay, fine. If you like subtracting fractions, that can be fun. But just for fun now, what's the binary expansion of 1/13?
There are no halves, there are no quarters.
That's true. But I don't want to do arithmetic anymore.
That's
I'm going to fold a piece of paper. Now, I'm going to fold it on the board. But what would I do? All I have to do is calculate the fold sequence. I have a theorem. Okay? This is a piece of paper. So I make my first guess. Okay? And what do? So now I have 12 over here, right? So I make a right fold. Okay, when I make my right fold, what do I have? This is going to be 7. Okay? So now what do I have? I have 7 over here, 6 over here, so I make another right fold, yes? Okay, and when I do that, I'm at 10.
Left fold.
Now I make a left fold, and where am I? 5.
Right fold.
Now I have an even number over here, so I make a right fold, and I am at 9, right?
Yeah.
And then in what? Another right fold, and I'm at
Oh my.
11. And then another right fold, and I'm at 12.
Oh my god, it's like pie. No.
Okay? So I've gone right, right, left, right, right, right. Now I'm here 12. Now I've got 12 over here, so I make another, now I make a left fold, right?
Yes.
And I'm at 6. Now I make a left fold,
More R's.
and I'm at 3. Now I have 10 over here. I make a right fold, and I am at 8. Now I make a left fold, and I'm at 4. I make a left fold, and I'm at 2. And then
We're
another,
done.
we're done.
Wow.
And I would repeat. So what does that mean?
I mean, 0, 0,
So R is 1, left is 0, and I go backwards. So 0, 0, 0. Yeah, I've got one too many L's in here. I don't count that last L, right? Because the 13th is bigger than the 16th. Okay, so there's a 16th in it. So it's L, L, L. So it's 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 1, 1.
Hooray, we found
Base
the
2. 1,
One,
2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12-digit repeating binary decimal. Yes?
So if you're using the folding algorithm,
Mm-hmm.
then it's always going to be a repeating decimal?
So odd numbers, that's an interesting question. Can an odd number be a terminating binary decimal? No, right? Because if you're adding up powers of 2 in the denominators, you only have zeros or ones, so you're adding up,
R's are 2.
there's, everything is going to be even. You can't hit an odd exponent. So it will always be repeating. So every odd, 1 over n, where n is odd, is a repeating binary decimal. Yeah.
Isn't 1 odd, but it's decimal in binary 1?
Okay, so that with that one exception, yeah, sure.
One isn't. What's up with the number 1?
No, but that's not a fraction, right? So a proper fraction. Okay? Yeah. Okay?
1 over 1.
1 over 1. That's the one exception to this working, but that's true. Okay? So now if you want to know what any, so what's 1 over 31? You could just figure this out. You do the fold sequence. I mean, it's a pretty long sequence, but you know, but it works. Okay? All right? I think that's awesome. Isn't this cool? I mean, is it? Okay. Now, so what else did you notice? Okay, so when we did 12 virtually, and I did it on the board for a reason, because it just takes a while to do folding paper, okay? But what do you notice here? Yeah,
That one has all the lines drawn on it.
I hit all the folds, didn't I? I hit every point in between. Whereas for 7, remember how 7 worked? I did 1, and then I hit 4, and then I hit 2, and then I repeated. All I hit was 1, 2, and 4. For 5, sorry, when n equals 5, I hit them all. I hit 1, then I hit 3, then I hit 4, then I hit 2. I hit them all. Yeah.
How's 17 gonna work?
What's that?
Coincidence that 1, 2, and 4 add
Yep.
up to 7? Probably not.
1, 2, and 4 add up to 7. Hadn't thought of that, but yes, that's true. All right, so let's see. 13, I hit them all. What about, well, 10 we wouldn't mess with because that's even. So what about
1 over 17.
1 over 17? Sure, let's do that. So I have 1, and then what? 9, right? And then that means that there are 8 over here. So 13, 15, 16, right? And then I'm going to go back 8, 4, 2, 1. I'm not going to hit them all.
Wow, so you have to repeat.
But why did you stop though?
Because he
The algorithm would start over. Okay? So if I started at 1, right, the first fold is going to get me to 9, and then I have 8 on this side, so then I go 13, and then 15, and then 16, and now I have 16 over here, so I go to 8, and then 4, and then 2, and then I'm back to 1, and I start over. Yeah?
I inject that hitting them all and not hitting them all is an alternating pattern between the next primes.
Okay.
So let's try 1.
Okay, so here we So here we hit them all, we didn't hit them all. What about 11? Did you do 11? So 11 is the next prime.
We like in 5th grade or something, like skip 2 grades or something.
Let's do 11. Let's try this conjecture. So here, that means I have 10 over here, so I go to 6, right? Which then I would go to 3, and then I would go to, yes, 7, and then there's 4 over here, so 9, 10, and then 5, 8, 4, 2. Okay, so I hit them all. 13, we hit them all, so it doesn't alternate. Let's look at 13 again. So here's what I'm going to, let's look at 13ths. So let's keep track of how many 13ths are on the left and on the right when I go through the algorithm. Okay? So I make my first start, and I have 1 on the left, 12 on the right. Okay? And then I make a fold. And when I do that, I end up with 7 on the left and 6 on the right. Okay? And then I do my next fold. I end up with 10 on the left, 3 on the right. Then I do a left fold, and I end up with 5 on the left, 8 on the right. And then I fold this guy, so I end up with 4, 9, and 2, and 11, and 1, and 12. Okay. So when I run through the algorithm, this is what happens.
Symmetrical.
Well, it's symmetrical, but that's one thing. So I've been told that somewhere in the deep, dark memories of your mathematical training, you learned about arithmetic modulo n.
Yeah, we sure did.
Wait, no,
Okay, so and I don't know what notation you use, but I'll go with this. So in Z13, okay, I can add and multiply,
Sorry, I'm too busy.
okay?
Holding origami.
So this is a nice example of a group. My favorite thing to do with this group, though, 13 being prime is very special because it means that you can, when you multiply things in here, you never get 0 unless one thing is 0, right? Yeah. 13 is bad luck. There are no 0 divisors in this ring. That's right. So in particular, if you throw away 0, you have 12 things left over, 1 through 12, and you can multiply all those things together. They form a group too. Okay, do you know about groups?
Yeah, we.
Okay, good.
Not every. Well,
Not all of them, but some of them, yeah.
Groups? Oh,
Sure.
yeah, bro.
I did that in some.
This thing is a group. So, so let's take a look at this. Let me start here. Okay, so I have 1, fine. I have 2.
Can we rip the paper?
This is 2 squared. We don't need to work with paper. So this is 2. This is 2 squared. This is 2 cubed. Okay, now what's 2 to the 4th? Well, that's 8 times 2 is what? 16. What is 16 modulo 13? 3. Okay, so now what's 2 to the 5th? Well, that's 2 to the 4th, which is 3, times 2 is 6. And then 6 times 2 is 12. This is 2 to the 6th. 12 times 2 is 24, but that's 11, modulo 13. 11 times 2 is 18. Sorry, 11 times 2 is 22, which is 9. 9 times 2 is 18, which is 5. 5 times 2 is 10. And then 10 times 2 is 20, which is 7. And then 7 times 2 is 14, which is 1.
Right.
Yeah.
Why does it do it backwards?
I'm just going backwards through here. I mean, I started at 2 and I started raising things to different powers. Okay, so what I got here was that if I started with 2 and I took all the powers of 2, I got every non-zero thing.
Right.
Okay, there's a name for that. Here's the fancy math name. It means that 2 is a primitive root. Nope, you don't have to take notes. In fancy, that's the fancy words. 2 is a primitive root of unity modulo 13. What that means is you take all the powers of 2, you get every possible non-zero thing modulo 13.
I'm using the abbreviation from
Yeah, mod. Use mod if you want. Now, let's take a look at 5. So 5, remember, we got every fold too. So on my left and my right, I started with 1, and then I had 4, then I had 2, and I had 3, then I had 1, and I had 4. And then I had 2, and then I had 3, and then I had 1, and then I had 4. Okay? So this is the same chart for 5. So what do I get? I get 2 squared, 2 cubed is 8, which is 5, sorry, is 8, which is 3 modulo 5. And then 2 to the 4th is 16, which is 1 modulo 5. So 2 is a primitive root of unity modulo 5. What about 7? 7 seems like bad news, right? Because I started with 1 and I had 6 over here. And then I got 3 and 4. And then 2 and 5 and then 1 and 6. So now I got 2 squared, and 2 cubed, and that's it. It starts to repeat again. So here, 2 is not a primitive root of unity, modulo 7. Okay? Do we have a conjecture? Yeah?
2 isn't the root.
In 11, you hit them all. I bet if you write down this chart for 11, you'll discover that 2 is a primitive root of unity modulo 11.
Okay, so 2 is a primitive root of unity modulo n, then
Yeah. Yeah.
Yeah, what he said, except
Yep.
since it goes 2 ways, at least it seems to,
Mhm.
go with if and only. I would dare to go with if and only.
If and only if. Okay. So you hand me an odd integer n. The idea now is that 2 is a primitive root of 1 modulo n, if and only if you get every fold. That's the conjecture. It's actually a theorem. Did you learn something?
Yeah.
Okay.